Alright, let's start working on number 13 here. We've got a hexagonal table that by itself seats 6 people, 1 person at each side. And then we're adding tables onto this. And so the question is, if 50 people can sit at the row of tables, how many tables are in that row? And 13. This is a linearity problem. We've got this problem where we start with 6, and then each table we add, we get 4 more. And so on. And there are 2 ways to solve it. The first is brute force. Right? We could just keep adding a table and add 4 and check. So it'd be, 10, or, we'll start with 6, 10, 14, 18, 22, and so on until we get to 50. And we could have this chart where it was, table 1, table 2, table 3, 4, 5, or we could see that what we're developing is this form of a y equals mx plus b, right? Where m is the slope of a line, right? We've got this line growing, here's the slope, right? That slope is, how many, it's this ratio, right? Delta x, delta y. M equals delta y over delta x. In this case, right, when x changes by 1, that's tables, people, right? We're seeing that we have 4 people per table. So m equals 4 over 1, or equal 4. So we'll say that y, right, which is people, equals 4x, equals tables, after the first, plus 6. And so we know that 50 equals 4x plus 6, or that would be equal to 44 equals 4x, or 11 equals x. So remember, x is tables after the first, so we have to go back and say that tables, right? Tables equals x plus 1. Tables equals x plus 1, or t equals 12 tables are in the row. So we can put the answer up here, 12 tables. And it's obviously, in the amount of time it took for us to solve this algebraic equation and set it up in that form, could we have just brute forced it? In this case, brute force is probably somewhat comparable, right, to solving it out. But let's say we had 350 people, okay? Brute force starts to take a much longer time than what it takes to just, have this line here and to solve it based on that information.